Okay, thank you very much for the introduction. And first of all, I wanted to welcome all of you guys for coming to the conference. I'm happy to see all of you, and hopefully we'll have a productive 5 days here. So in this talk, I want to talk about spin transport and coupled quantum magnets. And the particular physical quantity that I wanted to focus on is noise in spin current. Noise in spin current is flowing across weakly coupled quantum magnets. And let me just start off by collaborating. This work was done by my PhD student who just started last fall, Josh Aftergood. I'd also want to thank the internal funding agencies from CUNY. Okay, so I want to first start off by giving a very big, broad introduction, then go into talking about some brief history about spin current noise. And then motivate why it's interesting to look at noise from the point of view of charge current, because that's probably what's more well studied so far. And then I want to look at noise in two different types of systems. First one in a large S magnon system, and then the second one for spin-a-half quantum spin chains, and compare and contrast the noise in these two types of systems. And I'll talk about different types of biases you can apply. I'll define the spin Fano factor, look at manifestations of the quantum statistics of the tunneling spin excitations in the noise, and then look at experimental extraction of spin Fano factor. And I'll summarize at the end. Okay. So a lot of excitement in the recent years in spintronics is emerging out of this collection of phenomena known as spin Hall phenomena. Essentially, this effect allows macroscopic magnetoelectric coupling between electrical currents and magnetization. And it's typically studied in bilayer systems where you have a paramagnetic metal coupled to a magnetic system. And there's a family of effects like the spin transfer torque and inverse spin galvanic effect, which allows electrical currents to induce magnetization dynamics. And then there's the inverse effect, with spin pumping and inverse spin Hall effects, which you can use magnetizing dynamics to generate electromotive force in the adjacent normal metal. And these kind of effects and the experimental demonstration of these effects, I think, are opening up nice new area where you can study two-terminal spin transport through electrical insulators. And so I'm sure many of you are experts on this, and we'll hear a lot of talks in these kind of involving these kind of heterostructures. But let me just say that in this kind of setup, what you have is a paramagnetic metal with strong spin-orbit coupling, and by passing a charge current through this, the magnetoelectric coupling allows one to generate spin current in the adjacent magnetic system. And generate magnons. And these magnons diffuse through this magnetic insulator. And if the spin diffusion length is long enough for those magnons to reach the other side, then those magnons can be collected in the platinum metal, the second one. And that spin current can be detected through electromotive force that it generates. And so this kind of two-terminal spin transport through insulators is detected as non-local current drag that is mediated by diffusing magnons in the magnetic insulator. And so far, a lot of interest has been looking at how the spin propagates through here, and a lot of details we will see in this conference as well. What I'd like to do in this talk is to focus on the noise in this spin current, and what are the interesting things one can learn by looking at the noise. So if you dig some literature, some of the earlier works about noise in spin-active systems have been studied from Mischenko and others in early 2000 or so. And the focus there initially was on looking at actually noise in the charge current, but in a spin-active system, like a spin valve system. So they were looking at the noise in the charge current as a function of how the relative orientations of the ferromagnets changes in this kind of spin valve heterostructure. And then there were other set of studies where they were looking at quantifying non-equilibrium spin accumulation in a spin valve setup by measuring noise. So this set of works I would sort of classify as spin-dependent charge current noise. So the focus was still on charge current noise. but in a spin-dependent system. And then there were other works like this one, theoretical work, where there was a ferromagnetic system with a precessing magnetization, and this pumps spin current into two adjacent normal metals on both sides, and theoretical work studying autocorrelation function of the spin current as well as cross-correlation of the spin current in this kind of setup. And there was also work with Akash as first author, and I think collaboration with German group and maybe Tohoku as well, where they were looking at equilibrium spin current noise in conductors. So they were looking at equilibrium spin current noise in platinum, which is coupled to a magnetic insulator, and they saw this oscillation in the noise, equilibrium noise signature, which is reflecting the underlying spin Hall magneto resistance effect. And so by doing this, they showed this manifestation of fluctuation dissipation theorem. And then more recently, some focus is now going towards looking at spin current noise in insulators as well. And Akash has done some work on this, and I think in this session he'll give us a nice talk on this, so I won't go into too much details. My focus is also here as well. So I also want to look at spin current noise in these insulators, but my focus will be on one-dimensional quantum magnets. Okay, so why is it interesting to look at noise? And maybe to motivate that, I want to start off by just talking about basics of current noise in mesoscopic systems. So imagine you have a very simple circuit like this. You have a voltage, a resistor, and a current meter here. And if you, then you have average current, basically. So the current meter will measure some average current, but then there's always some fluctuations about this average current, which is time dependent. And the noise spectral density is defined to be the non-local time correlation of these current fluctuations, the Fourier transform of that. And there's always noise existing in the system, even in equilibrium at finite temperature. And this was first measured by Johnson in 1928, and it was theoretically explained by Nyquist in the same year, in back-to-back papers in Physical Review. And so let's imagine a case when voltage is 0, average current is 0, but the noise spectral density, essentially, there's a white noise, almost frequency independent noise in the background, which is proportional to the temperature and also proportional to the conductance of the system. And so by looking at noise, basically you can get information about the conductance, which is the information you could have gotten by just doing a current response, looking at the current response. And so this is actually a manifestation of a tight relationship between random fluctuations in the system and the response of the system, which is just a manifestation of fluctuation dissipation theorem. But if you actually go to a non-equilibrium situation, you can get even more information from the noise. So imagine that you have a setup like this where you have a metal which has an impinging noiseless electrical current. It's impinging this a tunnel barrier which is quite strong, let's say, and you have another metal on the other side. If this barrier is strong, most of the electrons get reflected, but some go through stochastically. And the fact that these electrons are transmitted through this barrier in a stochastic way generates noise on this side of the system. And one of the first people to look at this problem was Schottky in 1918. And Schottky found that the noise on this side is just current times the electron charge. And this result can be understood quite simply in the following way. So the current can be written, the average current that arrives on this side could be written as E times the average number of electrons that go through this barrier over some characteristic timescale tau. But then if you make the assumption that the tunneling events are completely uncorrelated and the tunneling processes obey Poissonian distribution, then the fluctuations in the number of electrons that go through is equal to the average number of the electrons that go through. So the noise, which is just the fluctuation in the current squared, average value, is just E squared times this variance over tau. And if you just make the replacement of this variance equaling the average number, you get E squared n over tau. and that's just E times I. So this is just nothing but Poissonian random uncorrelated tunneling of electrons through this strong tunnel barrier. And so you can understand it in this way. However, electrons do have correlations, and the most obvious correlations are fermion statistics. And to understand that, you can use the Landau-Büttiker formalism to understand how that arises. So let's incorporate the fermion statistics, but we still ignore interactions between the electrons. So you basically have a non-interacting electron system, and you have, let's say, n conducting channels. Then the conductance through the Landauer formula can be written as 2e squared over h times the sum over all the transmission probabilities of the existing channels. And if you do a little bit more work and calculate the low frequency noise through this system, and assuming that the tunneling probabilities has an energy dependence that is varying on a scale that's much larger than the temperatures and the voltages that are involved in the system, then the noise can be written in this way. And so there's an equilibrium piece and then a non-equilibrium part, which depends on the voltage of this applied across the system. And there's Fano factor F, which essentially is a ratio of transmission probabilities of the channels. And if you go to the equilibrium limit where voltage is much less than temperature, then you can reproduce Johnson-Nyquist result. But if you go to a large voltage regime, the noise approaches F times the Schottky's result, F times EI. And if the transmission probability is low, where T is much less than 1, then the ratios cancel out, and F approaches 1, and you can reproduce exactly Schottky's original result. But this Landau-Büttiker formalism allows you to kind of transition between equilibrium and non-equilibrium limits and incorporate Schottky's original Poissonian result. And so one thing that's interesting in these in this formalism is that you can actually, or looking at non-equilibrium noise, is that one thing you can do is reveal the statistics of the particles that are carrying the current. And one thing you can notice is that if you have n channels in the system and each channel has pretty high transmission probability, then you could see that the Fano factor is going to vanish because the transmission probability is close to 1. And so every time a new nearly ballistic or nearly 100% transmitting channel opens up, then the Fano factor vanishes. So as you get these 2e squared over h steps, every time you get a new step, there was an experiment, this is actually an experiment, that showed that Fano factor actually vanishes, that every time you open up a new channel. So this is experimentally observable, and so and you can actually reveal the fermion nature of the electrons in a nice way. So this 1 minus n, Tn factor is really coming from the fermionic statistics of the particle. The other thing that non-equilibrium noise can reveal is the charge unit of the charge carriers. So if you go now to the limit where T is much less than 1, the Fano factor approaches 1, and you get noise is equal to E times I. And this E is nothing but the quantum of charge that is carrying the electrical current. And there were really nice experiments done looking at tunneling of Cooper pairs. If the elementary excitations which are carrying the current has 2e charge, then experiments showed that actually the noise can be doubled in the non-equilibrium limit. And then if you go to more exotic systems like fractional quantum Hall edge states with a Laughlin sequence, in that case, theory predicted that there are quasi-particle excitations which have fraction of an electron charge, 1 over odd integer. And the presence of those fractional charges was also observed in very nice transport experiments and by looking at the Schott noise. So another thing that non-equilibrium noise can reveal is the charge unit of these charge carriers. So we want to look at the similar thing with current noise, spin current noise. Can we look at similar physical effects in spin systems as well? So here's a cartoon of the type of system I'm interested in. Let's say you have a spin conductor on this side, which is carrying noiseless spin current that's coming in. There's a strong barrier here this barrier one can model as weak exchange coupling, let's say, between two spin systems. And then because of that, the spin quasi-particles may get reflected most of the time, but some may go through in a stochastic way and generate noise in the spin current on this side. And the question is, can we reveal the quantum of the spin excitations, the spin moment or spin unit of each of the quasi-particles that are tunneling through? And the other thing is, can we look at the statistics of the spin quasi-particles? And the statistics is relevant in this kind of setup because if you have a magnon system, so let's say you're looking at a large S system, then you basically have tunneling of magnons. And that's because you can inject basically more than one spin, one excitation into a single site at a time when you have a large S system. So the physics of tunneling of spin excitations is in terms of bosonic particles. But then if you go to a quantum magnet where you have spin 1/2 degrees of freedom, then if you flip a spin 1/2 system once, you can't flip it again. So spin 1/2 operators is inherently fermionic. So as the spin S goes from a large S to a small quantum limit, you have this transition from a bosonic-like tunneling physics to fermionic-like tunneling physics, and that should have also consequences on the noise as well. So these are sort of two issues that we want to address.
Excuse me?
Yes. Sorry.
So, can you give me some simple idea how this barrier should look like for an experimentalist?
So the way I see it is just some coupling between the two systems. So exchange coupling, let's say between two quantum magnets. Like if two magnets are close together, maybe the wave functions will overlap enough that there is some sort of exchange interaction. That's the particular type of interaction I'm thinking right now. Okay. Yeah.
So any energy barrier basically would kind of do this reflection.
Yeah, right. I mean, so imagine this coupling is very weak, so that a lot of spin excitations are impinging it, but the coupling is not strong enough to really allow that transmission to happen. Then you're kind of in a weak coupling limit or a large barrier limit. Okay. That's how I kind of see.
Is dipole interaction sufficient, or is that too weak?
No, I think there's many ways to couple two systems. I think one can also consider how dipole coupling can also, generate transmission through there. In that case, you have spin non-conserving interactions, so maybe it will give different signature. Here, it's SU2 symmetric coupling. So, that might give also interesting. And I think Akash actually might talk a little bit about, well, at least he has one paper on that, right? Where you include the effect of dipolar interactions and how that changes the shot noise, and very interesting result there.
I have a question. So here, still you need this two system to be magnet, cannot be non-magnetic material.
Right. Well, I'm not saying that you need to have long-range magnetic order. The system doesn't have to have long-range magnetic order. It can have spin-carrying excitations. As long as it has spin-carrying excitations, that's fine. It doesn't have to have magnetic order. In fact, the quantum spin chain doesn't have long-range magnetic order in 1D. And I'll talk about that. Okay. Okay, so the system that I want to look at is spin-1/2 one-dimensional quantum magnet. And an example is a well-known example is the XXZ quantum antiferromagnet chain. Which has this well-known Hamiltonian. And this model is particularly nice because there's a lot of it's amenable to rigorous theoretical analysis. So it's been studied very well, and several exact solutions exist. And also, it's experimentally relevant. There was NMR experiments showing very nice agreement between theoretical and experiment. And also recently at Tohoku Group, they demonstrated Spin-Zabik effect in quantum spin chains, I believe the strontium copper oxide material. And so showing that doing this kind of platinum and spin injection detection kind of scheme may also be applicable to these kind of one-dimensional quantum magnets as well. So motivated by that, let me just look at a simple setup like this, where you have two semi-infinite quantum spin chains which are weakly coupled by exchange interaction at this site here. And so I have two spin-a-half XXZ antiferromagnet chains. I'm going to assume that there is axial symmetry about the z-axis. So what I mean by spin current from now on is just z component of the spin current. I'm going to consider two types of biases. So first is chemical bias. So I'm going to apply a magnetic field on one of the spin chains so that I'm effectively increasing the chemical potential of that spin chain. And I can supply spin angular momentum by, let's say, attaching a platinum with a charge current on this side. And then this side is just the detector for spin. And what I'm going to focus on, and I'm also going to allow thermal bias between the two. So namely, I can change the temperature of the injection chain relative to the temperature of the measurement chain, so T1 and T2. So I'm going to allow two different types of biases. And the quantities that I'm going to focus on are spin current at this site tunneling across here and the noise in that spin current, as well as the spin Fano factor, which is the ratio of the noise to the current. The model is just this XXZ antiferromagnet chain. I'm going to allow an exchange SU2 symmetric coupling at the site, at the J = 0 site. And the long wavelength theory of this model can be modeled in terms of the Tomonaga-Luttinger model. And if delta is less than 1, it's quite well known that the Tomonaga-Luttinger model is the good model, the low energy limit of this model, and there's various irrelevant operators like umklapp scattering as well as band curvature effects. These things are all sort of RG irrelevant. So in the long wavelength, low energy limit, one can just work with this Luttinger model. And the velocity of the bosonic excitations as well as the Luttinger parameter, the interaction parameter, are known from exact solutions in Bethe-Ansatz. So you can use the results there. And I can impose the semi-infinity boundary condition by applying boundary condition properly on the bosonic operators. And then I can model the magnetic field bias by including this kind of term, an effective chemical potential, which couples to the Z component of the spin. So the theory is that, okay, so what I want to consider is the spin current and the noise that's tunneling across the two spin chains. So I can define that as the total spin that's leaving the injection chain, for example, and I can calculate that within Keldysh, which actually in this limit, in the low coupling limit, weak coupling limit, just essentially you can use linear response. Keldysh is actually equivalent to linear response. What we get is a spin current and noise in this way. So here the temperature of first chain enters here, the temperature of the second chain enters there. And then there's this factor which is characterizing the chemical bias in the system. And that's the current and that's the noise. And before I go into the details of this, and let me just first compare the result to the Magnon case. So for the Magnon case, I'm considering a similar system. Let's say I have two Magnon baths, and they're weakly coupled by exchange interaction. And on one side, I'm going to consider Magnons are in a quasi-equilibrium state at a chemical potential mu, which can be finite for a pumped Magnon system at temperature T1. And then on the other side, I have another Magnon system that's in an equilibrium state with temperature T2. And I just want to compute the current and the noise across this. I'm going to give a little bit of a gap in the Magnon system by applying a Z-component magnetic field. And so this is just a straightforward calculation. Once you go through, what you find is that in the large S limit, you have a non-interacting gas of bosons with this dispersion relation for a cubic lattice. And I'm going to write a general exchange coupling. And what you find is the current current that's flowing across this Magnon system is just given by these two expressions. And the noise is given by this expression. G of omega is the tunneling density of states of the Magnons. Okay, so let's compare the two results. First, I want to start off by looking at the spin Fano factor for the Magnons. Let's first consider the case when the Magnons are at the same temperature, but you bias the chemical potential of one Magnon system, but you bias it strongly so that it's much larger than kBt. Then the Fano factor, which is just the ratio of noise to current, actually approaches h bar, which is just like the Schottky result, basically saying that the Magnons are being transported across this coupled system in a Poissonian, completely random, uncorrelated way, because I'm not introducing any interactions between the magnons. So it's just going through in a stochastic, in units of h bar. But if you look at the other case, so this is kind of what we would have expected. But now let's say we apply no chemical bias, so the chemical potentials of the two magnon systems are the same, but then we apply a thermal bias. Then if this thermal bias, this dimensionless thermal bias, so it's T1 minus T2 divided by T2, if that parameter is much greater than 1, you can also push this system toward this Schottky limit. Basically, you can also induce this kind of stochastic tunneling of magnons, completely uncorrelated, by applying a thermal bias as well, a strong thermal bias. And so you can get F going to H bar. And so in either case, a large thermal bias or large chemical bias, you can push the system toward this Poissonian tunneling of magnons, each carrying a spin quantum of H bar. And that's just a pictorial representation of the result. For the spin chain case, it's a bit different. So if you apply a large chemical bias, much larger than temperature only, so the temperatures of the two spin chains are the same, you can reproduce Schottky's result, F going to H bar. Basically, the exchange interaction between the two spin chains are only allowing spin 1 excitations to go across. The quantum spin chains, the eigenstates of the quantum spin chains are not magnons. But because the exchange interactions only allows spin 1 excitations to tunnel across, the Fano factor approaches H bar again. However, if the chemical bias between the two spin chains is the same, but then you apply a large thermal bias, the Fano factor diverges as long as the chemical bias is 0. And this divergence of the Fano factor can be understood in the following way. If we're in this limit, low energy, long wavelength limit, where the Tomonaga-Luttinger model is a good description of the quantum spin chains, then what we find is that the spin current will vanish if the chemical potential bias is 0 for any temperature T1 and T2. Of course, this can be changed if those irrelevant operators play a role, some perturbative role. But as long as we throw away those irrelevant operators, basically the current vanishes or any T1 and T2 as long as mu is equal to 0. Notice here that the chemical bias effect completely decouples from the thermal effects. So if mu is equal to 0, this whole integrand is killed. And so I just vanishes completely, but the noise remains. So Fano factor is just noise over the current, so that diverges. And this is kind of a consequence of throwing those irrelevant operators out. Of course, they play a perturbative effect. At finite temperature, these irrelevant operators do not completely flow to 0, so they do play some role. So it will be interesting to look at how Unklapp processes and band curvature effects will renormalize this result. But at least to lowest order, if we throw those away, this is the result we get. Now let's focus on the noise itself without looking at current and noise, but just the noise itself. And I want to consider two different cases. So first, I want to look at the quantum spin chain case. Imagine that I have one spin chain that is heated at a higher temperature compared to the other, and I calculate the noise. Then let's say I heat both spin chains, and I calculate the noise again. And if I take the ratio between the two, the noise when you have two heated quantum spin chains is larger than the noise when you have one heated spin chain. That's kind of understandable. If you heat the temperature, you just increase the Johnson-Nyquist noise. You're increasing noise. However, if you have, let's say you have one spin chain case which is chemically biased, but the other spin chain which is not chemically biased, and they're both at the same temperature, you calculate the noise. And let's say they're both at the same temperature again, but you chemically bias both systems. Then the noise actually is reduced when you non-excite both spin chains with the non-equilibrium drive, as you see here. So this noise actually goes down. And this kind of behavior is not observed in magnon system. If we do the same calculation for the magnons, if you heat both magnon system, the noise will go up. And if you non-equilibrium bias both magnon gases, the noise will also go up. And I think that this sort of reduction in the noise is due to the Pauli statistics of the underlying excitations, which are tunneling. Namely, if you look at the exchange interactions between two quantum spin chains, it's actually nothing but hopping of Jordan-Wigner fermions. If you map the quantum spin chains to Jordan-Wigner fermions, you can just rewrite this as a hopping of fermions. It's not like hopping of magnons, which are bosonic, but this is fermionic. So if you chemically bias only one system, there's phase space for fermions to scatter across, and so you generate more noise. But then if you bias both spin chains, then the phase space is pinched off, and the fermions don't have phase space to scatter across the chains. So that reduces the noise. And of course, this kind of Pauli blockade of occupied states is not relevant for both magnon systems, which are bosonic. Okay, so one last thing. How do we experimentally try to extract noise? So let's come back to this setup where we have coupled quantum spin chains, and let's see what's the noise here. So let's first consider the spin current noise just at this point right of the spin chain where the spin just gets injected. I'm going to make a rather violent assumption that that spin current, no additional noise is created as it goes through. Namely, the detector is detecting exactly the spin current that's impinging here. So let's say we make that assumption. Then the spin current noise just at this interface is equal to the equilibrium noise due to just Johnson-Nyquist of the detector metal. Plus, there's some effect due to the coupling to the spin chain, which also has equilibrium noise. So those are two equilibrium contributions. And there should be noise here, which is due to the noise that's coming from this non-equilibrium part, which propagates down. The noise will propagate down and arrive at this point. So there's some additional noise that's generated by the non-equilibrium bias. And so if one measures the total noise first in the presence of the bias, and then you turn off the bias and measure the noise again and take the difference between the two, one should be able to quantify the excess noise, which is exactly the noise that we computed here at the coupling site. And it's reasonable to assume that that excess noise will be proportional, and the noise will just convert into electrical noise in a proportional way. So I just write the excess noise as excess noise that one sees electrically to be some constant theta tilde times the excess noise at the tunneling site. The current also converts by spin Hall effect into electrical current, and we can also assume that the impinging spin current is proportional to the electrical current that you measure in the platinum contact. So if you take the charge Fano factor that one measures in the charge current that's generated in the platinum metal, then it's S over I that I computed, but some unknown prefactor, which one has to somehow extract. And one can extract this prefactor if we first go to this large bias limit, because in this large bias limit, we know that S over I approaches H bar. So if you first take your system to this limit, you can extract this prefactor by going F over H bar. That's just the charge Fano factor that one can measure divided by H bar. That's that prefactor. And once you have this prefactor, then one should be able to get the spin Fano factor over the whole parameter regime. Okay, so let me just summarize. I hope that I was able to convince you that spin current noise can tell us something about the underlying statistics of the particles which are carrying the spin excitations, and it also can tell us about the spin unit of the tunneling spin excitations. And I think what we want to do now is look at the effects of these irrelevant operators. How do that renormalize these results, like Umplatt processes and band curvature and all these things that take us away from the Luttinger limit. And then I also be interesting to really build a microscopic model properly for how spin current noise that's impinging the platinum contact, how it actually gets converted to noise, electrical current noise in the platinum contact, so that one can make a direct comparison between what I basically computed and what can be measured in a lab. I think a more microscopic, detailed model of that is really necessary to quantify this properly. So that's sort of the future outlook. Okay, so thank you very much for your attention.